Okay, now let's consider what happens if we have 2 points, let's say 10 meters apart. That's kind of poorly written, but it says 10 meters apart. We have waves of wavelength 1.5 meters emanating from this point and from this point and spreading out in all directions. We assume that the waves are produced in phase. That is, when this one's at a peak, this one is simultaneously at a peak. When this one's at a valley, this one's simultaneously at a valley. If this is water waves, we could imagine a plunger of some kind moving up and down here and linked to a plunger down here that moves up and down at the same time, so that the waves come out in what we call in phase. Peaks matching, peaks coming out at the same time, valleys coming out at the same time. Of course, a wave, peak, then a valley, peak, then valley. Now we're interested in what is going to be observed over at a point here. Okay, now this point lies above or below the axis of symmetry here, the axis of the the axis of symmetry for the 2 points, and that axis, of course, is a perpendicular bisector of this segment here. So we see the perpendicular coming out here, and it's implicitly at the halfway point between the 2. The question that we want to ask is, well, this wave travels further to get to this point than this wave does. Okay, so if D2 represents this distance and D1 represents this distance, and how do we calculate D2 minus D1? And also, how many wavelengths does that correspond to? Because if these distances are different, that means that even though the wave started out in phase with peaks matching peaks and valleys matching valleys, since this one travels further to get there, we might have a valley of this wave arriving at the same time that a peak from this wave does, due to the difference in the distances. And the thing that's going to determine that is how many wavelengths that distance comprises. Now let's assume that this point is, for starters, 2 meters from this axis of symmetry. Then we want to determine how many wavelengths of difference there is in the 2 paths. Okay? And then we want to make a sketch of the 2 waves when the first one is arriving with a crest. Well, the paths are fairly easy to calculate. We can construct 2 right triangles. Remember, this point is 2 meters above this. These points are 10 meters apart, so that if we bring this point straight over, it'll be 3 meters below this originating point and 7 meters above this originating point, giving us a right triangle here with a hypotenuse of the square root of 30 squared plus 3 squared, or 30.15, using the 30-meter distance. I don't think I mentioned, but it was labeled in the other figure. And here, using the Pythagorean theorem to get a distance of about 30.8 meters. Now that's a difference of about 0.65 meters. I really should have my units marked on that. So let's see. Okay, it's 0.65 meters. How many wavelengths is 0.65 meters? Well, we said the wavelength is 1.5 meters, so that path difference is path difference over lambda, 0.65 over 1.5 meters, or 0.43. So that the wave traveling this path will be 0.43 of a complete wave behind this one. Now what's that going to look like? Well, this isn't a real well-drawn picture, but if this wave comes in and arrives at a peak along its path, then this wave is going to come in and it's going to be near a valley, because it's going to be 0.43 wavelengths behind this one. That's almost half a wavelength. And of course a valley is half a wavelength behind a peak. So if we compare this wave as it comes in, it's almost half a wavelength behind this one. Now, how far is it behind? Well, half a wavelength would correspond to 180 degrees of phase, because if we go through 360 degrees, our wave goes through a complete cycle. So that if this is the original wave coming in, arriving at a peak, the red wave is the wave that's lagging behind, and it's behind by about 0.43 of a wavelength. That means its peak is 0.43 of a wavelength behind this one, and it's going to be near a valley here. To see exactly how far the waves are out of phase, well, it's 0.43 of 360 degrees out of phase, which is about 160 degrees, or 0.43 of 2 pi radians. Remember, when we don't have a unit on the angle, it's in radians, or 0.86 pi radians out of phase.